Hello everyone, this side Ankush. I'm currently pursuing my BSc Honours Electronics from Acharya Narendra College, University of Delhi. I, on behalf of Department of Electronics, present a tutorial video to design and obtain the frequency curve for the first order active Butterworth low pass filter having lower cutoff frequency FZ in Hz using IC 741. I would like to thank our teacher coordinator, Professor Amit Garg and Dr. Ravneet Kaur for providing me such an opportunity. So, I have divided this virtual lab in 5 parts. First, we will be looking at theoretical concepts in which we will be covering the basics of op-amp and low-pass filter circuit. Then, we will be looking at the working formula, in which we will be covering the basic formula and voltage gain equation. Then we will be designing the circuit and using components like capacitor, resistor, power source, and lot more components, and that will be covered up in Multisim Setup. Then we will be plotting the graph and taking the readings from that simulator, and we will be plotting it through MS Excel. At the end of the session, we will be looking at results and observation and calculate the roll-off factor. So let's jump to the first part, which is theoretical concepts. So here we have the first basics of IC 741 op-amp operational amplifier. The 741 op-amp IC is a monolithic integrated circuit, comprises a general purpose operational amplifier. It was first manufactured by Acharya Semiconductor in the year 1960. The number 741 indicates that this operational amplifier IC has 7 functional pins, 4 pins capable of taking input and 1 output. IC 741 op-amp can provide high voltage gain and can be operated over a wide range of voltage, which make it best choice for use in integrators, summing amplifier, and journal feedback application. It also features short circuit protection and internal frequency compensator circuit built in it. This op-amp IC become in the 8-pin DIP package. So here I have posted the picture of this op-amp, so you can see the basic structure, how the IC look like. So let's begin to the further application. So here I have a little bit explained about the first order low pass filter using op-amp. The first order low pass Butterworth filter is realized by RC circuit using along with an op-amp. Used in the non-inverting configuration. The circuit diagram is shown in the figure given in the upcoming slides. This is also called as one pole low pass Butterworth filter. Thus, the low pass filter performs the opposite function to that of the high pass filter. Hence, the first order low pass Butterworth circuit filter circuit can be obtained by interchanging frequency determining resistance and capacitor in the high pass filter circuit. So here you can see the diagram of low pass Butterworth low pass filter. So here you can see we have input voltage, which is connected in series with the resistor, which is further parallelly connected with the capacitor. So here we are giving the input in the non-inverting terminal. Further, we can see the inverting terminal is connected with the feedback, which is named by RF resistor, and further connected with R1, and this combination of RF and R1 decides the gain of this op-amp. Here we have connected plus VCC and minus VEE, and it is usually Then we have the output, which is represented by VO and further connected with the ground. One terminal is connected to V out and another is connected to the ground. Let's look at the working formula. So here we have the equation which says VO, which is V output, that is output voltage, divided by V in, that is the input voltage. So that's ratio is nothing but the gain, is equal to AF. AF is the gain of the filter in pass band, and that is divided by this whole equation, which is 1 plus J F divided by FH. So where F is the frequency, current frequency, and FH or FL, it should be written as actually FL. So that is the lower cutoff frequency. So here FL, it should be FL is equal to 1 by 2 pi RC, and that is equal to low cutoff frequency of this filter. Here AF is given by the 1 plus RF divided by R1, and that is nothing but the gain of the filter in the pass band. And here you can see the V in is nothing but the input at the non-inverting terminal, and VO is the output. So I hope you are clear with the circuitry diagram and basic equations. So here we have the final equation, which can be represented as VO divided by Vn is equal to AF divided by under root 1 plus F divided by Fn. Here you can see the behavior of the low pass filter, which can be observed from the above equation. So here if we have the we are giving lower frequency, that is the frequency is less than the cutoff frequency FH, then the output gain is almost constant and is equal to the value of AF. When it is at the cutoff frequency, then you can see it is equal to that gain is equal to AF divided by under root 2, which is equal to 0.707 AF. This is at the cutoff frequency. When we have the frequency greater than the cutoff frequency, at higher frequency we will get the gain is less than the value of AF. So that is basically the behavior of the low pass filter circuit. And here you can see the graphical observation which we will be getting. We are expecting this type of curve, and here you can see we have frequency on the x-axis and voltage gain on the y-axis. Voltage gain is nothing but the magnitude of V out divided by V in. So here we have AF, so it is constant till this part below the frequency HF. HF is nothing but the cutoff frequency. Below cutoff frequency we are getting the constant gain, which is equal to the magnitude of AF. At cutoff frequency we are getting the gain which is equal to 0.707 AF, and above cutoff frequency, when we are giving frequency above the cutoff frequency, then we can see this, there is decrease in the gain. This decrease is nothing but the roll-off factor, which is further calculated and I will show you that how it is calculated in the upcoming slides. That rate is usually the rate of decrease is 20 dB per decay. Decay basically indicates it is decreasing, and if we calculate the slope, that is minus 20 dB per decay. And this frequency, cutoff frequency, is also noted as 3 dB frequency, which is important question from the Viva point of view. It is generally asked from the examiner. Next, let's look at the general observation which we can draw from the graphics which we have seen. So thus the for the range of frequency, if greater than 0 and less than the cutoff frequency, the gain is almost constant, and which is equal to AF, and is the high cutoff frequency. And then at the cutoff frequency, which is equal to when we are providing the frequency equal to cutoff frequency, then we have gain reduced to 0.707 AF, that is also known as 3 dB down from AF. And as the frequency increases, then HF, the gain decreases at the rate of 20 dB per decay. The rate, which is 20 dB per decay, means that the decrease of 20 dB in a gain per 10 times change in the value of frequency. I hope you're clear with the above points. Further, what we can observe that the same rate can be expressed as 6 dB per octave, but here what we can see that is the decrease of 6 dB per 2 times the change in the frequency. So that is for the 10 times change in the frequency, we can see the change of 20 dB, and when we are looking at the 2 time change in the frequency in that region, then it will be 6 dB, and it is known as 6 dB per decay octave. Here we have HF, which is also called as cutoff frequency, break frequency, and minus 3 dB frequency and corner frequency. These are the different names given to the same thing, which is cutoff frequency. It's another important question from Viva point of view. So let's jump to the multisim setup. In order to save time, I have already designed this circuit on multisim. You can easily make this circuit, and there are many videos available on YouTube how to design the first order low pass filter, so you can take help from it. Otherwise, I have given you the basic idea how the circuit will look like. I will simply let you know the setting. So here you can see the AC sweep. So first you need to select this portion for the active analysis and setup simulation. Once you click, further window will pop up, and here you can see an active analysis. You need to click on AC analysis. Here I have already changed the value, but it will be default in your system if you are doing it for the first time. So here first you need to start frequency should be 1. You can keep it as 1 hertz, or you can even keep it as 0 hertz. Then we will go up to 5 kilohertz, and the sweep type will be linear, and the number of points will be 150. You can increase or decrease the number of points according to your wish. Vertical scale will also be linear. This was all about the frequency parameter. Then click on the output. Here output we will be taking VO, that is V bracket 7 divided by V8. V7 here in my circuit is nothing but it is representing the output, and we are dividing it with the input, which is here represented by the 8. This number might be different in your circuit, so you just need to check it out and add the expression accordingly. Here you can add and remove the equation, edit the equation, so that you can do on your own. Once set up with the output, then you can here see the default setting which are there, and this is about the summary of all what we have. Let's click on the first you need to save, and then you can click on the run button, and here you can see here we have obtained the graph. Here we are not interested in studying the phase, so we can simply delete this graph, and here we have the magnitude graph. So that is pretty much similar to what we were expecting, and here you can use cursors. Here you have the graph, and use cursor to mark the appropriate value of cutoff frequency. That you can do on your own. It is an analysis part. So once this was all about the graph and the circuit which was required. So here you can see the circuit. Here you can see the circuit, and here we have the sample graph which we should opt. So let's begin to the next part. After multisim setup, we have to take readings, and I will be sharing you the practicals reading which I have observed. The practical, I was doing the same experiment in the practical. Let's jump to the practical observation which I have received. So here is an observation table, and here we have given the input voltage Vi is equal to 2 volts peak to peak, and it was fixed. And here we have taken around 25 readings, and here I have given the column for the input frequency. This is column for the input voltage, and the input voltage almost remain constant, but it's do get fluctuated. So it's better to write the input voltage. Although fluctuation is not that much, it's a 0.0 value, so that fluctuation is okay when you're doing in the practically, but although it should be avoided. And then we have the output voltage, then we have calculated the gain, and further we have calculated the magnitude is equal to 20 log the V out divided by Vn. So here we have the observation table. So I have calculated the cutoff frequency. Here you can see the cutoff frequency. I have marked this cutoff frequency with the marker. The yellow highlighted part is cutoff frequency. Then I have calculated the dB per octave, that is the roll off factor, and I have selected the dB per octave method. So I was not having that much. Calculated at 2.5 kilohertz and then at 5 kilohertz. This is the observational graph which you will get. So that is pretty much good when you compare it with the ideal graph. So I have made this graph on MS Excel. This is the circuitry implementation which we have, the graph which we have obtained there, and the cutoff frequency was around 1.8. Here we have received the cutoff frequency 1.4. So that variation do occur when you're doing in the Multisim and the practically. So obviously we don't have the exact value. So this was all about the observation, graphical observation. So let's jump out to the results and observation. So here we have the results, which is the cutoff frequency. The theoretical cutoff frequency is 2.842 kilohertz, and the experimental cutoff frequency is around 2.4 kilohertz. And here we have the relative error of around 15.55%. And this is how I have calculated the roll off factor, and that may vary from person to person how you are calculating. I have just given you the rough height. Okay. Here in the roll off factor, the theoretical value was this, and the experimental value for IC 741 was this, and we have gotten a relative error of 7.05. Let's sum up our virtual lab. Here what you can see that the frequency response is plotted on the semi-log graph, and the theoretical and practical cutoff frequency calculated are 2.842 kilohertz and 3 kilohertz. There's a difference, little bit difference the value, and the theoretical and the practical roll-off factor in dB per decay is around 20 dB per decay for the theoretical value and 18.858872 for dB per decay for the practical. So the references which I have used in this virtual lab is Electronic Hub, is another website which is good one and providing the resources to study, and another we have used is the first of the low pass Butterworth filter from eeeguide.com, and then the one of the most favorable book which you might have named you have earlier heard of is Op-Amp and Linear Integrated Circuits by Ramakant A. Gaikwad. So that was all about this tutorial video, and I hope you have gained some knowledge and know a little bit about the practical. Thank you so much for listening patiently.